Hi guys, I'm Mrs. Hobbs from the STEM Academy,
I'm Mrs. Keel, also from the STEM Academy.
and we're here today to talk to you about wave structure. There are two main types of waves, electromagnetic waves and mechanical waves. The electromagnetic spectrum is something that you're probably very familiar with from your textbook in high school or maybe even in middle school. The electromagnetic spectrum starts off with radio waves and runs all the way through to gamma rays. In between, we have several other varieties of waves, all dependent upon wave frequency. The only part of the electromagnetic spectrum that we are able to perceive as humans is the visible spectrum. We can feel infrared waves when we go out into the sun, but we can't actually see them or manipulate them. But the visible spectrum is what we're most familiar with, but it is only a tiny little portion of the electromagnetic spectrum.
Mechanical waves are something that we probably have seen a lot more and interacted with, and there are three types. Longitudinal, related to sound, made up of compressions and rarefactions. Transverse, which are the ones that you think about when you think of a wave motion that have crests and troughs. And then surface waves, related to what we think about when we see the ocean and crashing on shore, or the waves that move along the surface when an earthquake occurs, obviously relating to what's happening at the surface.
We're going to take a quick look at a little video from NASA on the electromagnetic spectrum.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers. the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
All right, here we have a little GIF of an electromagnetic wave. As you can see, it moves in both directions at the same time. It goes up and down and side to side. The up and down is the electric field, and the side to side is the magnetic field, and they propel one another through space, which is why electromagnetic waves can travel through space, but mechanical waves cannot, since they need a medium to vibrate. So let's talk a little bit, or let you get to know a little bit about what we call mechanical waves or traveling waves.
Hello, I'm Patrick Stewart. Did you know that right now?
Here we have an ordinary piece of rope. It's not one of those magician's ropes that can mysteriously be put back together once it's been cut in half. And it's not particularly strong or durable. But you might say that it does have special powers because it's going to demonstrate for us the physics of traveling waves. Ropes and strings are really good for this kind of thing because when you move them back and forth, the movement of your hand travels through the rope as a wave. By observing what happens to this rope when we try different things with it, we'll be able to see how waves behave, including how those waves sometimes disappear completely. How's that for a magic trick? This is a typical wave, and waves form whenever there's a disturbance of some kind. Often when something about the physical world changes, the information about that disturbance gradually moves outwards, away from the source in every direction. And as the information travels, it makes a wave shape. Think about the disturbance you cause, for example, when you jump on a trampoline. When you hit the trampoline, the downward push that you create moves the material next to it down a little bit too. And the same goes for the material next to that, and so on. And while that information is traveling outward, the spot where your feet first hit the trampoline is already recovering, moving upward again because of the tension force in the trampoline. And that moves the area next to it upward too. This up and down motion gradually ripples outward, covering more and more of the trampoline. And the ripples take the shape of a wave. Waves are made up of peaks with crests, the bumps on the top, and troughs, the bumps on the bottom. They have an amplitude, which is the distance from the peaks to the middle of the wave. They also have a wavelength, which is the distance between crests, a full cycle of the wave, and a frequency, frequency, which is how many of those cycles pass through a given point every second. Multiply the wavelength by the frequency and you get the wave speed, how fast it's going. And the wave speed only depends on the medium it's traveling through. That's why the speed of sound, which is a wave, doesn't depend on the sound itself. It doesn't matter how loud or quiet it is, it just depends on whether the sound is traveling through, say, air or water. Now, there are 4 main kinds of waves, and we can use our rope to show the difference between some of them. A pulse wave is what happens when you move the end of the rope back and forth just one time. One lonely crest travels through the rope. That's the pulse. Then there's the continuous wave, which is what happens when you keep moving the rope back and forth. In that case, your hand is acting as an oscillator. Anything that causes an oscillation or vibration can create a continuous wave. Now, things that cause simple harmonic oscillation move in such a way that they create sinusoidal waves, meaning that if you plotted the waves on a graph, they'd look a lot like the graph of sine x. But the waves we've mainly been talking about so far are transverse waves, ones in which the oscillation is perpendicular to the direction that the wave is travelling in. When a wave travels along this rope, for example, the peaks are perpendicular to the rope's length. The same thing was mostly true for the waves that you made on the trampoline. The waves were travelling along its surface horizontally, but the peaks were vertical. But there's also longitudinal waves, where the oscillations happen in the same direction as the wave is moving. In the case of a longitudinal wave, the back and forth motion is more of a compression and expansion. These are the kinds of waves that you get by compressing and stretching a spring, and they're also the kinds by which sound travels, which we'll talk about more next time. But all waves, no matter what kind they are, have something in common. They transport energy as they travel. At a microscopic level, waves occur when the movement of one particle affects the particle next to it, and to make that next particle start moving, there has to be an energy transfer.
Okay, so we wanted to stop the video there because it starts to get into a lot more of physics-based type of things, and we want to kind of keep this as simple as possible and relate it strictly to wave formations. We have a couple of Phet simulations that we've done some screen recordings on, and Ms. Keel is going to talk you through those.
This first one relates back to looking at what waves are and giving you an introduction into them. So you have different tools that you can use. You've got a measuring tape, you've got a timer, you have this little other magnifier so that you can see what's happening, so it gives you a generation of what the wave formations are happening. So you can turn on the water and you can adjust the frequency of the wave that's occurring and its amplitude. And you can turn off to see the graph of the wave so that you can see the crests and the troughs. And as you move through the Phet simulation, you can set up all of these tools. I'm going to move across this a little bit so that we can look into what's happening. So as you turn on the water, you can actually adjust with these to see the distance between where the wave is beginning, where it's starting to oscillate, and where it's moving outward. And this is giving you a recording of how big of the wave, as it's moving through. And then you can get your good view of what's happening with the water as it's changing and what's creating the wave as it's rippling across the surface of the water. There's even a top and side view that you can see of the wave as you move through. And you can make it normal speed and you can slow it down as well. I'm going to move through this a little bit more. This would be the side view of the water as the drops are falling and as they're moving and making the waves as it's making the ripples. Sort of similar to the video where she showed jumping on the trampoline and you saw the downward motion and then the rippling effect across the surface of the trampoline. And then you have your sound wave that you can also do the same with and turning on your features. You've got the same tools that you can manipulate. You can look at top view and side view again and have this control and manipulation of what's happening. And then there's also a laser that you can use with the light wave, the pulsating and going through, which is kind of cool. So again, these are all manipulations that you can do for an introduction into waves. There's also the waves on a string. Now, this is going to give you more of the movement and what you would see with mechanical waves, specifically your transverse. So you can see you've got your oscillator here. You can turn on for it to be manually done with the nice little clamp. And then you have your your C-clamp on one end, and you've got, looks almost like a little mini one over here. And you can have a fixed end and a loose end. I'm going to move through this a little bit more. Obviously, your manipulation of what you choose to do. Something called damping and tension can also be adjusted. Damping is with waves what can cause it to start to slow down and decrease. Your tension can be how taut that you are pulling on what you're trying to make your wave through. You also have your rulers and timers that you can use. And then you can make it have no end. You can just, it could be a wave that goes on forever and ever and ever, which can be a lot of fun. So that's what's going on. I enjoy using the oscillator because then you can manipulate the height, your amplitude. That's from your resting position that will give you your crest and your trough. And then you can also adjust the frequency that it's happening. So those are your Phet simulations. Yeah.
All right, so what we're going to do now is we're going to show you a couple of things that we do in the classroom with our students on using things that they have created and an object that we have purchased. Now, this first demonstration, put together straws. There's a link online where you can go and learn how to make these, but they're pretty basic. You just space your straws out evenly, and then you run a line of tape across the top and a line of tape across the bottom. And then when it's all nice and taped together so it doesn't fall apart, you can get a partner, stretch it out, and you can tap it on one end, and you can see the wave move through the straws. And you can also just simply twist, and the more that you twist, the more waves that you create. And then you can kind of look at it. This would represent a crest, this would represent a trough, back to a crest, back to a trough, and you can kind of see like a frozen in time view of a wave. Okay. Most of you guys are probably very familiar with slinkies. And slinkies are a lot of fun, but we have a really, really super long slinky. And with this, we can actually model some fairly good wave formations. Do you want to start and I'll hold? Okay, so this is a fixed end, and you can see the wave bounces back to the origin point. Okay, or if we are both moving it at the same time, we can get a wave that actually interferes with the other wave. And if they interfere together and create a larger wave, it's called constructive. And if they interfere in a different direction, it's called destructive. And you can see they don't make a very nice pattern with a destructive. This is when you're in the cafeteria and everybody in the world is talking all at once and nobody can hear anything because the waves are they're destructively interfering with one another.
But when you make a nice wave pattern and it's working together, for example, maybe when you go to listen to music and it's supposed to sound really good and it's working together, that would be more of what's going on there. This is also, you can talk about related to what's called a standing wave, and when a wave pattern is repeating itself and continuing.
Okay, one thing you might want to notice about this is if you have a nice continuing pattern, your eye sort of gives you a little optical illusion where it almost looks like it's rotating rather than going up and down. Let's see if we can get some really fast waves going through here. You have to have really good arm muscles for this, and I don't. But you can see how it almost looks like it's rotating. All right, woo, that's more
We've got to get our damping in effect.
That's
so
right.
Get those waves calm back down.
All right, well, I hope you guys have learned something about waves today, and I hope you can go play with the Phet simulations, and also Crash Course Online, where that little video came from, is a really excellent resource to help you understand many, many science topics. See you later.